Okay, the final limit equilibrium technique we're going to look at are a set of methods which we call complete equilibrium procedures. But we'll primarily focus on one of those, which is called Spencer's method. Okay, to go back to the general method of slices, the summary we saw on the unknowns and equations. The total number of unknowns we have is 5n minus 2. The total number of equations we have is 3n. In each of the other techniques, we've made more than 5n minus 2 assumptions, but if we only make 2n minus 2 assumptions, just enough to make the problem statically indeterminate, then we have 3n unknowns and 3n equilibrium equations. Therefore, we call it a complete equilibrium procedure. And so the first assumption we always make is the n location of the normal forces, and we assume that acts through the middle of the base of the slice. And that leaves us with n minus 2 assumptions still required. So, Spencer's method. This is the most common and most popular of the complete equilibrium methods. And with Spencer's method, we represent the side force as a resultant z, and with acting at an angle theta. And the simplifying assumption we make is that the side forces are parallel. So we have a single theta value. Therefore, our number of unknowns, that this part right here reduces from n minus 1 to 1. And we end up with, and we've also gotten rid of the n locations of n. So now we're left with, if you add what's left up, we have a total of 3n unknowns. Okay? So, since the side forces z and zi, we end up, we're acting at the same angle. Since they are at the same angle, we combine them into a single resultant side force, qi, acting at that same angle. Then he assumed that W, S, and N all act through the center of the slice through point B, which is shown in red there at the base of the slice. Therefore, in order to have stability, moment equilibrium for that individual slice, Qi also has to act through the center of the slice, or excuse me, through that point B. So we go back to our overall moment equilibrium equation, and these are the moments. The WR sine alpha is basically the sum of the moments caused by the weight of the slice, and S times R is equal to this shear force along the bottom of the slice times the moment arm, which is R. And if we then, since Q acts through the base, and it has to be equal to the sum of W, S, and N, we're just going to work in terms of Q. And if we look at the components of Q, both perpendicular to the base of the slice and parallel to the base of the slice. Perpendicular to the base, it's Q times the sine of alpha minus theta. And parallel to the base of the slice, it's Q times the cosine of alpha minus theta. And so if we sum the moments around the center of the circle, the component of Q parallel to the base of the slice is what acts, because the component perpendicular goes through the center of the circle. We can neglect that. And so we get the sum of the moments is equal to the sum of R times Q cosine alpha minus theta. And then for overall force equilibrium, looking at, again, just dealing with this resultant force Q, we get the sum of Q sine alpha equals theta equals 0. And then for the horizontal direction, the sum of Q cosine theta equal to 0. But since theta is a constant, it's the same for every slice, and so you can bring it outside the summation. And once you do that, you can divide both sides by sine of theta. And down here, you can bring cosine theta outside the summation and then divide both sides by cosine theta. And so both of these equations just simplify to the sum of Q is equal to 0. All right, so then by summing the forces on individual slices, you can derive an equation for Q in terms of the known quantities, W, delta X, C, prime, tan phi prime, etc. And you can come up with this equation for Q that has F in 3 different places, interestingly. And now we have 2 equations, sum of Q cosine alpha minus theta equals 0, sum of Q equal to 0, and 2 unknowns, F, factor of safety, and theta. And so, and again, this value of Q is what you plug into these individual equations. And so yeah, then you can solve it iteratively and solve for the factor of safety F. If you have non-circular shear surface, you, instead of summing the moments about the center of a circle, you come up with a local coordinate system and then sum moments around the origin of the coordinate system, where your moment arms are YB and X sub B, as shown here. But again, that gives us 2 equations and 2 unknowns. So that's that's Spencer's method. Again, as I mentioned before, it works great. It's very popular. But there are other complete equilibrium procedures. There's the Morgenstern and Price method, which basically, instead of assuming that the side forces all act at the same inclination, it derives a relationship between the shear force X on the side and the normal force E, which is a scaling factor times some assumed function. And the normal force acts at the base of the slice, satisfies complete equilibrium. It's more work than Spencer's method, and it gives about the same results. Hence, people generally use Spencer's method. Chen and Morgenstern method is very similar to this. It just has a different functional relationship between X and E. Thought to better represent the side force relationships at the end. And then there's another one called Sarma's procedure, which the shear force, interslice shear force X, is related to shear strength using some scaling factor and a function. And this is developed for applications for seismic stability, and therefore it includes a seismic coefficient. And again, satisfies complete equilibrium. So if you look at tables 6.2 and 6.3 in the textbook, there's a summary of all these different methods. But Spencer's method is often the preferred method and typically the default in most slope stability software, including Utexis. It's accurate. It's the simplest of all the complete equilibrium methods. It does require iteration, but it iterates very quickly, and can be used for both circular and non-circular surfaces, so it's very flexible.